development styles. So, thank
you. Hello. So, I'm a game engine developer by trade, so I'm a bit more technical than most in the serious games community. And even in the regular games community, which is where I usually work in, most are now just using the big game engines. And as I like to work on game engines myself, I always start my talks with pointing out the problems with those engines. And Unreal is now in the bigger games the mostly used engine by far, I'd say. But if you want to develop something for a broader audience that also runs in web browsers, that doesn't really work anymore. They basically gave up on that years ago. If you use Unity, you know what happened last month, probably.
something happened.
Yeah, and I'm very much looking forward to whatever will happen with it next year. And yeah, that probably. And of course there's only one real solution to that. And that's a book cover, so it has to be right. And besides working on games, I also help other game developers with building their own game engines, and I especially focus on the sillier aspects of that, which is usually making your game engine run on different platforms, which can be surprisingly complicated. And by far the most complicated aspect of that is your GPU. And I like to show pictures of how your GPUs actually look even in your office computers nowadays. That's an Apple M1 chip, and I chose an Apple chip because they don't care all that much about games. So I could have shown the PS5 chip instead. But this is basically a mid-level office picture-making computer chip. And if you have a closer look, can you see my cursor? No, you can't. But you can see in the lower left, the blue blocks, that's your actual CPU. The Apple devices, it's always just one big chip which has everything integrated. So the blue blocks are your CPU, the yellow blocks on top, that's your GPU. And you can see even in those smaller chips, that's already a bit bigger than your CPU. And in the more high-end chips, it's even much more actually. It's very yellow. And yet, most programmers don't even know how to program those. And they are not just used for games now. Of course, you need the GPUs for your graphics. It's also what's powering all the AI hype. It's actually what started it. And yeah, so let's talk a bit about how to program it, especially about how to program it in a way that things run on a lot of platforms, because that got even more complicated in recent years. And every platform has its own ways of doing that. And even if you have a computer with one graphic chip and then run a different operating system on top of that, suddenly you have to use a very different approach to make graphics work. And yeah, so Windows has its Direct 3D, Apple has their own API with Metal. Web browsers are always lacking about 10 years behind. So when you want your stuff to also run on the web browser, it gets especially complicated. Consoles have their own APIs, which I'm not allowed to talk about. And about 8 years ago, there was a split and different companies introduced new APIs, and it's now split like this. And usually when Microsoft or whatever introduces their newest version of Direct3D, it's about using the latest features in some new GPUs that came out a year earlier, or even at the same time. That's not what happened this time. Instead, these new APIs were all about the programming model, and especially how to synchronize your CPU work with your GPU work. Because that used to be mostly automatic, and your graphics driver did a lot of work. And developers of bigger game engines liked it less and less, because as the workloads for GPUs became bigger and more complicated, those automatic things that happened in the graphics drivers, they tended to lead to random stutters in the games, and that's not nice, because you get bad Steam reviews when that happens. And that's why those new APIs were really introduced. It's absolutely not about new features, it's about how you control when exactly what happens, and to have more control about it. And for that reason, it's actually possible to map the feature set of the old APIs to the new APIs and the other way around. So you can build some software construct where you program in the old style or in the new style and make it work everywhere. And that's what I wrote about in the paper, and I'll introduce the main examples of how to do that in detail. And the first thing you will probably run into when you use a newer API like Vulkan is that all your GPU resources, like textures, vertex and index buffers, that's where your data for your actual 3D meshes are stored. It used to be that you created something like a vertex buffer, and you could lock it and pump in data and unlock it, and then do a draw call that uses that data, and all of that worked automatically. And then you lock it again, update the data, unlock it, and draw it again, and things still worked. Nowadays, if you do that, you will have very fancy looking graphics, because the GPU will use your buffer while you write to it. Now you have to manually synchronize that, so you write into your data, then you issue a command for the GPU, and it starts working with that. Then from the GPU, you issue a fence, or whatever it is called in the different APIs, to inform the CPU that the GPU is done with this data and you can update it again. So you always have to synchronize manually. And the nice thing about that is, of course, you can really optimize this for your specific use case, instead of the driver having to guess what is going on. And you might maybe also know, when you're a PC gamer and a new big game comes out, usually you always also get a new driver from NVIDIA, which has some text in the release notes like optimized for latest game from that just came out or comes out tomorrow. This is also an aspect that became much less important with the newer systems, and this is one aspect which they really tuned for each big game, how the driver optimizes this resource usage and synchronization for the different games. And basically, I also already explained the most simple approach is that you update your buffers, and then you inform the CPU when the GPU is done, so you're waiting. But waiting, of course, is not what you want to make your game do. So the other approach that the drivers used automatically to some extent is to use a shadow buffer of your resources. So the GPU could work on one buffer, and when you want to lock the data again, behind your back, it created another buffer, and then you could write into the new buffer, and on the GPU side, it switched it out later. So you didn't have to wait. This, of course, becomes problematic when your resources are really big. So the driver did guesses based on resource size and then either created new buffers or waited. And this is also quite easy to implement yourself in a basic version. And that way you can map an old graphics API to the new APIs to run and program your graphics like you used to do it. And then you just create those shadows buffers in your code. And you can also very easily add a little bit of additional data for your code to know when it's appropriate to do that and when it's more appropriate to wait, or for what resources that's the case. The other way around is, of course, very simple. If you want to program with a newer model and you target an old API, you just ignore your synchronization primitives and do nothing, because that happens automatically later on. Then this one is especially nice because Unreal completely fails to handle this properly. When you program GPUs, you have those small programs that you actually upload to your GPUs and that run those. Those are called shaders for historic reasons. And in old APIs, it was actually tricky to see how the actual compilation of those shaders happen. And this compilation on PC and mobile, at least on not Apple mobile, happens at runtime because all the different GPUs use completely incompatible machine code for the shaders internally. So the driver has to do a compilation step before the code can actually run, because the games cannot be distributed with the final code. They use either actually source code or some form of bytecode. And in the old model, you uploaded your shaders, and then you were setting some GPU modes, like your blending mode that defines how partially transparent things happen, or your depth mode that you need for depth tests in 3D scenes. And the tricky thing is that depending on your hardware, part of those status bits you set in your API actually get compiled into your shader, because the hardware internally is like it's not as fixed as the API is, and they just map that to their more powerful GPU instruction set. But for that reason, things can happen just like it's on the slide, that the actual compilation is usually happening at the latest point possible, which means immediately before you do a draw call and actually try to bring something to your screen. Because the driver tries to collect all the data, because if it doesn't, and it compiles beforehand, and then you change the blend mode later, it maybe compiled something that's actually never used. So it usually, depending on how the hardware works, compiles earlier because it knows it doesn't really need it on that hardware for the shaders, or it compiles very late. And this compilation, again, leads to stutters. And the model for your APIs is, for that reason, very different. So instead of just setting state on your GPU, you create those so-called pipeline state objects, and you put your shaders in there, and you put all your different state in there, and then you run a compile command. And at that point, the driver is actually supposed to compile. And when you start up a modern PC game nowadays, for many of them you get a loading bar where it tells you it's compiling shaders. That's when the game is creating all of those pipeline state objects. But when you run an Unreal game, it still stutters during the game because they cannot tell what pipeline state is actually needed in their game because they didn't build their APIs that way. Which everybody is complaining about now, so better do your own engine. And the last point for today is multi-threading. Graphics APIs. It used to be so that most things could only be done from a single thread, and that's of course not that nice. Now we have 8 CPU cores or 16 CPU cores, and all the work in preparing data for the GPU actually amounts to a whole lot on modern complex games, and having that on only one thread can be a serious problem. That's also something that was changed for the new APIs. And in the older APIs, commands for the GPU were issued directly. So you had an actual function like draw triangles. And then it went off and hopefully draw some triangles. In the new APIs, instead you have structures called command buffers, where you put in commands, and at some point you can take that buffer and commit it or submit it or however it's called here and there, and then those commands will be transformed into what the GPU needs and will actually be transferred over or made accessible to the GPU, and then the GPU can run it. But the important point here is that the actual recording of the commands, that can be done on as many threads as you like. That's of course something that you can't really make use of that on the old APIs. But you can still build something so that you can use software that uses this kind of API to run on old one to make your game run in the web browser again. That first seems relatively complicated, but you basically rebuild the structure with your own command buffers. When those commands are issued to write commands into the command buffer, you can write your own little bytecode into some buffer structure, and when it's submitted, you can run like a little interpreter which then issues your real commands. That will not get you the performance benefits you have from the new APIs, because the command interpreter then still has to run on this one thread. You cannot get around that, but you can at least take something that's optimized for modern system and make it run on web browsers that way. And yeah, that way you can always map from old to new APIs in ways like this, because there's not really new features in those APIs. But and sometimes it's you get away with good performance still, but sometimes in this case, if your game is really CPU heavy due to your GPU preparation work, it will still be problematic in that browser. And implementations of these things are available in open source projects I provide, and those are also actually used in production in various projects. There's this RPG Playground thing in the middle that's similar to RPG Maker but runs in a web browser, so that actually targets WebGL. The thing on the bottom right, that's a game called Crosscode that runs on all the consoles and was a launch title on the newest Xboxes even. That also runs on the same technology. And the thing on the bottom left, that's called Armory 3D, that's a full 3D game engine that runs inside of Blender, so you can use the Blender tools to make your game. Yeah, that's it.
Thank you, Robert. Any questions for Robert?
Just a comment, Vulkan is a little bit more versatile because it also runs on Linux and it also runs on Mac if you
Yeah, the Mac simulation layer, that guy actually started out with part of my software in building that, but that's a layer on top, so it's kind of in a similar vein like my software, but implementing a standard. And Linux, I think I didn't list Linux in my slides, but Linux is very problematic for actually releasing a game because of the libc problems and stuff. And actually the most broadly used approach now to bring games to Linux is to distribute Windows games and run them in Wine and Proton. But yes, then it's actually useful to have a Vulkan backend in your engine, because then you have at least one part that does not go through a translation layer, or not as much. But yeah, Vulkan can kind of be used on macOS. There's some restrictions because not everything can be mapped to Metal. Can be used on Linux, on Windows, on Android. The translation layer, I think, can also be used on iOS. It can be used on Switch, actually. That is pretty nice. Switch supports OpenGL, Vulkan, and their own API. And it doesn't work at all on PlayStation and Xbox. But those are important too. For my bank account, at least.
All right, thank you. I think we are out of time for questions now, but we have a coffee break now, so